Mixing problems are quite common in engineering, and you can see here the sort of situation that arises that we need to deal with. Now we're going to use Q to represent the quantity of stuff in our solution. So dq dt is the rate at which that is changing. And of course we're mixing things up, so we need to investigate that. And we're going to use the fact that there's stuff coming in and there's stuff going out. And so dq dt to begin with is going to simply be the difference in the stuff coming in and the stuff going out. So the stuff coming in can be broken down into the concentration times the flow rate. These are usually in units such as pounds, gallons, minutes. The rate out is very similar, and again, this is imperial measures. We could also deal with metric units. So here's a typical problem that we might see concerning mixtures. So we'll take our formula, dq dt, rate in minus rate out, and see about computing. First off, the rate in. The rate in is the concentration in, which is given right here, times the flow rate in, which is also given right here. Now, the rate out is a little different story because the concentration of the stuff that's in the tank depends on how much stuff has come in. And so the concentration going out is not going to be a constant, as is the concentration coming in. So we have to represent that by the quantity Q. Now, we always have Q stuff in 50 gallons, since we have a 50-gallon tank. And so we use Q over 50 to represent the concentration. Now, the flow rate out is given here. Notice that the flow rate in and the flow rate out happen to match in this problem, which is an ideal situation because then we don't have to worry about, well, either we're going to drain the tank dry or we're going to overfill it, one or the other. And so our differential equation then would begin by looking like this. Now we'll investigate that a little bit to start with, not the least of which is something that we've talked about many times in the past, and that is, how about a particular solution that might be constant? So doing a little bit of algebra on the right side of the differential equation, we can see now that in this differential equation, the 300 minus 3q would be equal to 0 when q is equal to 100. Now, we referred to that earlier by the name constant solution. We also used another name for that, which hopefully makes sense to you in this particular context, and that is equilibrium solution. So here is the graph of the slope field, and notice that at x equals 100 we have a constant solution. Now that kind of tells us that if we start off with any solution below 100, as this is mixed and drained and more stuff is poured in, it's going to eventually reach 100. If we started out with concentrations above 100, again, as it's mixed and drained and more stuff poured in, the concentration is going to lower. Eventually, the concentration will become 100 and it will stay there. So now let's go through and solve the differential equation. We'll rewrite the right-hand side so that it's separable. We'll move the 100 minus q to the other side and integrate both sides. And then try solving for the q. Well, first off, let me point out that the 100 minus q in absolute values is the same thing as q minus 100. So we'll just use the q minus 100. Multiply both sides by -1. Let me again mention, even though this was a c, when we multiply by -1, it is still some constant, which we're again just calling by the letter c, not negative c. And what we're going to do is do the natural exponential of both sides and come out with q minus 100 equals ce to the -350th t. And we'll add 100 to both sides, thereby recovering our formula for q. Now, using the initial value, q0 equals 0, in the beginning it was pure water, we substitute 0 for t, 0 for q, and solve for the constant. So we have this differential equation that represents this particular mixture problem. And as you can see from the slope field, here is in red is the graph of the equation for this particular problem. And as you can see, in the beginning we had pure water. As we pour in our salt solution that contains 2 pounds of salt per gallon, eventually that is going to rise to where we have 100 pounds of salt in our mixture. 2 pounds per gallon times 50 gallons would happen to be 100 pounds of salt.